Hello everyone, welcome to Tales of Celestial Wanderers program. What goes on in our night sky? While many of us know some basic constellations that we can see in particular places at particular times, there are roaming hunks of rock out there that show up irregularly and capture our attention. What are they and how can you see them? Solar System Ambassador Terri McCormick will present on comets, asteroids, and meteors. This session will run about 45 minutes for presentation with a 15 minutes window for question answers. If you have any questions, please use our chat feature or question answers feature. We will get the answers at the end of the program. And welcome you all. And now I hand it over to Terri McCormick. Welcome, Terri.
Thank you so much, Uma. I'm going to go ahead and screen share now. And we can get going tonight. There we go. All right. Well, welcome everyone to a brief overview of some of the things that show up in our skies at night. My name is Terri McCormick, and I am a retired 7th grade science teacher from Troy. The first thing I fell in love with as a child was the Apollo space program. So it turned out to be a dream job for me to teach astronomy at Smith Middle School in Troy for 16 years. My students ended up helping NASA researchers analyze their data from experiments aboard the International Space Station and on the space shuttles. We video chatted with astronauts aboard the International Space Station. And my students took new photos of Mars' surface from the Mars HiRISE orbiter. They also built some microgravity experiments for the NASA drop tower in Cleveland, Ohio, among other things. So I tried to pass that passion for all things space on to my students. But since retiring, I have joined the NASA Jet Propulsion Laboratory's Solar System Ambassador Program, which allows me to continue to talk about space with people in communities around the North Metro area. I've done programs with audiences from pre-K to adults. So thanks to the Clinton-Macomb Public Library for having me. I'm happy to be here and talk a little about my favorite subject. Before we jump right into discussing our main topic for today, which is asteroids, meteors, and comets, let's make sure we have a good perspective on where these objects come from. This is a time-lapse image taken from the International Space Station, showing some city lights as the orange streaks in the lower right, and a lot of lightning, those bright white circles popping up all over in the atmosphere. The star wheel, or the tracks of stars over a time-lapse image, show the rotation of Earth as we spin in a relatively stationary spot compared to the faraway stars. We've been able to plot orbits of planets and locations of stars for millennia by tracking this movement over long periods of time. And over millennia, well-known stars near each other from our perspective on Earth became what we call constellations and took on larger-than-life stories in various cultures' mythologies. We all know at least a couple of constellations that we can pick out, those stars that are reliable markers in space and time, even though they are farther away than we can really wrap our brains around. Let's look at how everything is connected, starting with stars. Stars are where everything else in our universe comes from, even us. Stars, like everything, have a life cycle. This graph is called the Hertzsprung-Russell diagram, and it's a classification system for stars in our universe. The y-axis, going vertically, shows brightness with the brightest at the top, and the x-axis shows temperature with the hottest on the left in blue, like the hottest central part of a candle flame burns blue. And the cooler stars are on the right in red. These colors are visible when you closely look at stars in the night sky too. Most stars fall in a line through the middle there called the main sequence. The smaller stars are on the lower right, and they burn at lower temperatures and lower intensity, so they conserve their fuel. This way they live a lot longer, actually hundreds of billions of years. That's billions with a B. You can see our own sun somewhere in the middle there, near the boundary of the yellow and orange. It's a pretty average, ordinary medium star that will live about 10 billion years. It's billion with a B. We know our solar system is about 4.6 billion years old, so our sun is distinctly what we would call middle-aged. The hottest and brightest stars in the upper left are also the largest mass, and so have the most fuel in them. These most massive stars live an average of only 10 million years. That's million with an M. They're basically gas guzzlers. That's why they don't live very long. They burn through their fuel most intensely and burning out relatively quickly. This graph doesn't do the size of these massive stars justice. So here is a quick comparison. Oop, didn't want that on there. Our sun is barely a dot compared to the biggest known stars in our universe. Size accounts for a major difference in how these stars' lives end. For smaller stars, those like ours, most will slowly run out of fuel and burn out over the course of millions of years until there's nothing left but a cold, dead rock. But for those larger stars that burn most intensely, the nuclear fusion process in their cores will slow down over millions of years as their fuel begins to slowly run out until there isn't enough outward pressure from the fusion to support the star's own weight. Then it eventually collapses. When that happens, these stars will go supernova, exploding with the last gasp of their fuel. That explosion throws massive amounts of dust and gas outward into the universe. This is a photo of the Cat Nebula, which was actually identified as a supernova well over 1,000 years ago by Chinese astronomers. Pretty cool little fact. All of the gas and dust from the formation of our universe 16 billion years ago and from the recycling of material through the birth and death of large stars continues to travel through mostly empty space. But eventually, these particles will come close enough to other particles for the basic laws of gravitation to take over. Gravitational attraction increases in two ways: when mass increases or when distance decreases. So as things get closer together, they have more of a powerful draw to each other. So these particles will slowly draw together, creating larger groups of particles with more mass and more gravitational pull. Over eons of time, these form bigger and bigger clouds of gas and dust called nebula. Parts of these nebula become more and more dense until there's enough matter or mass to exert vast amounts of pressure in a very small area, enough to kickstart nuclear fusion, thus creating a new star. This is why nebula are also referred to as star nurseries. Remaining gas and dust will orbit around the new star, eventually coalescing and creating planets and moons. And boom, a solar system is born, and the life cycle starts anew. This is the ultimate recycling process. This picture is one of the most famous structures in space. It's called the Eagle Nebula, and the entire thing, which you can't see here, is over 70 light years across. Take a little closer look at this image. The pillars appear to have a pretty well-defined set of borders for the most part. This image is captured in what we call visible light, or the range of light waves that we can see. Here's the same image on the left. Now, the image on the right is the exact same view, but taken in infrared light, which captures heat from the stars. So we can see all the stars in the area. Those stars are there on the left, but they're obscured by the amount of dust around the nebula. This is an example of how much dust really exists in space. Consider that the next time you have to dust your furniture. You may be wiping up the remnants from the origin of the universe. Now, if you know anything about the periodic table, this is basic chemistry and shows all of the known elements in our universe, all the natural ones. There are lab-created ones. There's a total of 118 elements currently. So the black areas there are where they go on the table. Hydrogen and helium in the top row are the foundational building blocks of the universe, formed in the Big Bang. This fact is relatively undisputed among scientists and is backed up by evidence from leftover cosmic background microwave radiation from the Big Bang, dating to 16 billion years ago. That hydrogen and helium formed new stars, which then forged new, heavier elements in their cores from nuclear fusion. Those newer elements are listed farther down the periodic table. You can see this on the chart that the color coding explains what elements are forged in what type of stars. These elements make up everything in the universe, including the human body. So when famed astronomer Carl Sagan said, "We are made of star stuff," he wasn't being metaphorical, he was being quite literal. Sagan's original quote, oft repeated. Sagan was the most well-known astronomer of my generation because of his amazing ability to describe complex topics to those without the training and language to dive deep into the subject. His Cosmos TV series explained a lot of the universe to everyday people. His current day replacement is astrophysicist Neil deGrasse Tyson, who did a fantastic reboot of the Cosmos series a couple of years ago. I think it was in 2014. I highly recommend watching it. He is, in my opinion, even more eloquent and down to earth than Sagan was. We know that the stars, planets, moon, life itself on Earth, these are all things built at the elemental level in the bellies of stars. But that list is not all inclusive, as sky watchers are often surprised by other irregular objects showing up unexpectedly. We have 3 categories of items that we're going to explore the rest of the hour: comets, meteors, and asteroids. There are a lot of projects out there investigating asteroids and comets. One of the newest and most exciting is Lucy, which launched just this past October 16th. The name is a historical nod to our important ancient ancestor named Lucy, whose 3-million-year-old fossilized skeleton was found in 1974 in Ethiopia and is pictured on all of the NASA mission logos, like in the upper right corner of this image. Finding Lucy, the fossilized skeleton, connected many dots in the evolution of hominids, our ancestors, to Homo sapiens. The Lucy mission will likewise explore fossilized remnants of our solar system, the asteroids. Lucy will travel to at least 7 asteroids over 12 years, collecting data from these fossils of our solar system to continue putting together the story of how we got here. More on Lucy later. This is a diagram from the Center for Near-Earth Object Studies, or CNEOS, showing the inner solar system and the known asteroids and comets that reside closest to us. CNEOS has identified 33,000 near-Earth asteroids that are over 3 miles in diameter. Those are big. There are over 1 million smaller asteroids in our solar system, and about 2,000 new ones are discovered every year. The largest known asteroid is named Ceres, It's about a quarter the size of the moon, and that's 600 miles in diameter. And it lives in the main asteroid belt between Mars and Jupiter, shown here. The main asteroid belt, or MAB, is one of two main places asteroids reside in our solar system. The other one is outside this image, but you'll see it on the next slide. It's called the Kuiper Belt, and it's located past Neptune. There are also two lesser known groups of asteroids that are in Jupiter's orbit, as you see here. They're called leading Trojans and the trailing Trojans. They lead and trail behind Jupiter. You'll also notice there are scattered comets here in the inner solar system, which are classified as Jupiter family comets because they are mostly affected by Jupiter's gravity. They orbit around the sun in less than 20 years. On the left, you can see the orbits of all our planets and the Kuiper Belt that is outside the orbit of Neptune. The Kuiper Belt holds comets as well as asteroids. On the right, you'll see an expanded picture where far outside the Kuiper Belt, but still within the gravitational tug of the sun, is the Oort cloud. This is where many of our known comets reside. Whereas asteroids are hunks of rock and metal, comets are a combination of rock, ice, and frozen gases. So with all these objects floating around our solar system, one might question, aren't there a lot of dangers of impact with Earth? Well, space is a very, very big place. Impacts happened a lot more frequently in the early days of our solar system than they do now. Early in our formation, objects traveled in random directions, so many collided with each other until the only ones left were all traveling in the same direction. Same uniform direction. So now there are far less collisions. It's kind of like separating the different directions on a freeway. It leads to a lot less accidents. So after everything settled out in the early formation of our solar system, this is a simple diagram of what's left. You'll notice that the standout in this image is the orbit of the comet. Comets are coming from the spherical Oort cloud beyond our planet's disk-shaped orbits. They have very long, stretched out elliptical orbits. As they near the sun, their ice starts to sublimate. That's changing directly from solid to a gas without going through a liquid state. You may notice sometimes your ice cubes, if you leave them in your freezer, will do the same thing. They don't turn to liquid. They just kind of disappear, going from ice to water vapor, solid to gas. The solar wind from the sun blows these gases away from the main part of the comet. So these comets' tails will always show up pointing away from the sun, whether or not the comet is headed towards the sun or away from the sun. So sometimes its tail is behind, and sometimes its tail will be leading the head of the comet. Comets are sometimes referred to as cosmic snowballs. When a comet's orbit brings it close to the sun, it heats up and spews dust and gases into a giant glowing head, larger than most planets, called a coma. The dust and gases that form the tail can stretch for millions of miles. These are likely billions, there are likely billions with a B of comets orbiting our sun in the Kuiper Belt and the Oort cloud. The current number of known comets, however, is 3,738, I think is what we're at. In naming designations, you will notice the name of the person who discovered the comet, along with a letter number combination. The P means it's a periodic comet, and periodic comets have an orbital period around the sun of less than 200 years. The C designation means it is a long period comet and not expected to return to the inner solar system. These are the most common ones, so they don't come into our neighborhood very often. When comets' orbits sling them around the sun, they leave a trail of dust and gases in their wake. Every year, the Earth passes through some of these debris trails, and the individual particles collide with our atmosphere, where they disintegrate and create fiery streaks in the sky known as meteor showers. We'll come back to meteors in a bit, but these are a few examples of recently studied comets. Comet Giacobini-Zinner is a small comet with a diameter of only 1.25 miles and an orbital period of 6.6 years. It's a Jupiter family comet, just like Comet Tempel 1 is also a Jupiter family comet. It orbits in 5.5 years. Comet Hartley 2 is small. It's approximately 1 mile in diameter and peanut-shaped. Hartley 2 orbits the sun within the asteroid belt, which makes it a Jupiter family comet. Its mix of gases, though, create very interesting emissions. Carbon dioxide-driven jets shoot from the ends of the comet, and water vapor shoots from the midsection. Its orbit is just under 6.5 years. Comet Swift-Tuttle is a larger comet with a diameter of 16 miles. Its orbit is 133 years, so we'll return to the inner solar system again in the year 2125. Hold on to your hats for that one. Comet Burrelli has a diameter of 5 miles and resembles a chicken leg. Jupiter family comet again, but its orbit loops in and out of the orbits of Mars and Jupiter. So it takes 6.9 years to orbit once. Comet Halley is often called the most famous comet because it marked the first time that astronomers really understood that comets could be repeat visitors to our night skies. Observations of Halley go back 2,000 years. Its orbital period is 76 years. Halley was last seen in 1986 and will return again in 2061. So hopefully some of you will be around to see that. Comet Hail Bop is my personal favorite because it was so visible. It is referred to as the Great Comet of 1997. Its diameter is 37 miles. It's about 5 times the size of the object that helped lead to the extinction of the dinosaurs. Due to its large size, this comet was visible to the naked eye, no telescope, no binocular, for 18 months in 1996 and 1907, appearing as this large greenish blob in the sky. It takes Hail Bop about 2,534 years to orbit the sun once. So we won't be seeing that come back for quite some time. Comet Shoemaker-Levy on the left is most famous for its collision with Jupiter in 1994, leaving an impact on the gas giant that was visible for quite some time. The comet actually broke up before impact so that multiple fragments hit the atmosphere, creating quite a show for astronomers. Comet Lovejoy was the most recent display seen from Earth. Its exquisitely long, beautiful tail distinguished it among more recently visible comets, but it was primarily visible in the southern hemisphere. Its orbital period is about 680 years. Then we have the discovery of our first interstellar object, which has been anticipated for decades. Oumuamua is often referred to as a rogue object because it came from outside our solar system, the first time we've documented this. Its name is Hawaiian for a messenger from afar arriving first. This odd-looking object has been tough to categorize. Originally, it was classified as a comet, but then observations revealed no signs of cometary activity after it slingshotted past the sun in 2017. So it was briefly reclassified as an asteroid until new measurements found that it was accelerating slightly, one of the few other signs of cometary behavior. So it was reclassified as a comet. It's the first of a brand new designation, the letter I for interstellar. It's now headed out of our solar system, tumbling end over end at 59,000 miles an hour. This is what makes science so interesting, having to rethink definitions based on new data. So will we soon see a new definition of a comet as something other than a dirty snowball? Or will we see Oumuamua get reclassified as an asteroid again, or as something completely new? We'll have to wait and see on that. The second use of the designation I was used in 2019 for Comet Borisov. This comet is referred to as a rogue comet because it came from outside our solar system. Astronomers found that the comet's tail was 14 times the size of Earth. It's considered pristine because it has never encountered the damaging radiation and solar wind from our sun. So its composition is, they're very anxious to study because it's very similar to the material that originally formed our solar system 4.6 billion years ago. Scientists theorize that a massive planet in another solar system shifted Borisov's orbit enough to cause it to travel in our direction. Here is a table of comet sightings over the last 350 years. Notice the irregularity of observations and the periods of gaps. We are in such a gap now, with the last visible comet in the Northern Hemisphere being in 1997, and the next one not scheduled until 2061. So how do I see a great comet with my own eyes? Wait 40 years for Halley's return, or maybe there's another way. We can see comet particles frequently and reliably, if not the whole comet. Meteors are the visible streaks of particles that burn up in our atmosphere. Sometimes they're just random rocks floating in space, but sometimes they're those pieces of comet debris left behind from a comet's tail that then intersects with our orbit, so that we regularly cross paths with this debris trail on every trip around the sun. That's why we have reliable annual meteor showers. Meteoroids, like asteroids, are these objects before they enter our atmosphere when they're out in space. Meteoroids are the smallest of the three categories of space objects that we're looking at tonight, 3 feet in diameter or less. They can be found throughout the solar system. Meteoroids experience incredible pressure when they enter Earth's atmosphere, and that pressure shatters them, transferring energy to the atoms and molecules in the atmosphere, which then release that energy by glowing. And this glow is what produces the bright trails of light in the sky that we see as meteors. There are 3 different names that we use to describe these smaller space objects. They are meteoroids when they are out in space, meteors when they're moving through our atmosphere, and meteorites are the remains that reach the Earth's surface, which doesn't always happen. Most of the time they burn up in the atmosphere. Small meteorites that reach the Earth's surface occur about 30,000 times a year, mostly dust-sized particles, resulting in an astounding average of 200,000 pounds of space debris added to Earth's mass daily. Again, I encourage you to think about the bigger picture when you have to dust your house. There is wonder everywhere, even in household chores. Michigan has had its share of found meteorites. The recent January 2018 fireball that exploded over Southeast Michigan, I was lucky enough to see that through a window wall at home. It left some pieces strewn across frozen lakes, so were easier to find, as this excited Royal Oak resident discovered. This meteor explosion created a shockwave of 2.0 magnitude as measured by the U.S. Geological Survey. Christie's auction house estimated this chunk, weighing less than 2 ounces, to be worth over $10,000. A piece of this meteorite became a part of this woman's engagement ring. But this is not the first time that a meteorite has been made into bling. There are a lot of amazing things about King Tut's tomb, but his space dagger is possibly the most extraordinary. It's pretty impressive that this was forged before the Iron Age. Iron is a big component of many space rocks, but most meteoroids and asteroids are made of just plain old rock called chondrite, sometimes combined with metals. It's very rare to see a solid iron nickel space rock, but they are exquisite. This all metal meteorite sample on the left was found in Mexico. Metal from space has really intriguing striations that occur during crystallization, and that's that striping you see that's embedded in the metal. Much more common are the stony iron combinations, which I think are beautiful, but the most common are the stony chondrite compositions at the bottom. Well, these are fairly large chunks that survived atmospheric burnup in falling to Earth. Remember that these are categorized as small space rocks to begin with. So let's look at much bigger ones. Asteroids, classified as a space rock with a minimum of 6 feet in diameter, minimum. Space is a big place and there's lots of room for objects moving around, but what happens when these larger objects do come across Earth's orbit? Larger space rocks intersecting with Earth's orbit occur only once every 10 to 20 years and can create major shock waves by heating up and exploding in the atmosphere. Russia has experienced the 2 largest asteroid explosions in recorded history on Earth, both in the last 113 years. In 1908, an approximately 5 megaton explosion, the equivalent to 5 million tons of TNT, occurred over Tunguska in Siberia, creating a shock wave so dramatic that it flattened an estimated 80 million trees. Now, the Chileabinsk Meteor of 2013 was a global event because it was recorded from multiple angles on many outdoor security cameras and the ever-present dashboard cameras in Russia. The airburst was briefly 30 times as bright as the sun and visible up to 100 miles. 2% of observers reported a sunburn. 28% felt warm watching the sky show. The meteoroid broke up over 20 miles above ground, producing a massive shock wave that broke out windows in 6 cities. And it left a trail in the sky, that top image there, that persisted for quite a long time in an otherwise cloudless sky that day. You'll see the hole, it landed in a lake bed. So it, in the lower left there, that is the hole in the lake bed from it. And then the remains of it that was retrieved from the bottom of the lake in the lower right. This particular rock was a surprise. Now, we didn't see this one coming because it came directly from the direction of the sun. Therefore, it was entirely blacked out by the sun's glare. Fortunately, that's rarely the case, but we'll return to detection methods a little later. Suffice it to say, we learned from this episode. First, let's take a look at some of the evidence of major impacts in Earth's history. The most recent large impact that we're aware of was also the most recent find due to melting of the Greenland glaciers. About 12,000 years ago, a 10 billion ton space rock slammed into Greenland, leaving a crater nearly 20 miles wide. The most famous crater in the US is Behringer Crater, or more commonly referred to as the not very original name of Meteor Crater. It's located just off Interstate 40 outside Winslow, Arizona. If you detect a somewhat vertical line to the left of the meteor in the right side image, that is Interstate 40. It's very close to the freeway, very easy to get to. It's relatively new. It's about 50,000 years old and over a kilometer across. Scientists estimate that the original asteroid was about 150 feet in diameter. Quebec hosts two pretty famous craters. The one on the left is 1.4 million years old. It does not connect to any other water sources, so its sediments have remained untouched, making it a fascinating scientific study. The lake ring on the right is the remains of the sixth largest known crater on Earth. It's over 43 miles across. As this is seen from space, you can see the wing of the space shuttle in the lower left of the image. The largest crater found on Earth is 300 miles wide. It lies hidden more than a mile beneath the East Antarctic ice sheet. Its age, size, and location also suggest that it could have begun the breakup of Pangaea, the supercontinent of old, by creating the tectonic rift that pushed Australia northward, marking another major event in Earth's history. The image on the right is a gravity anomaly map. It measures changes in the density of rock in an area due to impact. And you can kind of make out the colors in a circular ring pattern. This image reveals the crater's age at about 250 million years old, the same age as a massive extinction event, the Permian era extinction event, when 95% of life on Earth died out. Then there's the impact everyone knows about, Chicxulub, the impact most likely responsible for the extinction of the dinosaurs. There's nothing visible on the surface today, but modern imagery shows a gravity anomaly map on the left. The Yucatan coastline is the white line. You can see the rings of the crater straddling the shoreline. And white dots are sinkholes in the limestone around the largest of the rings. The date of the Chicxulub impact coincides precisely with a major change in geologic time between the Cretaceous and the Tertiary periods. This impact event caused a tremendous amount of matter to be thrown into the atmosphere, blocking out all sunlight for a few months before most of the particles dropped out. But enough particles remained suspended to effectively block 3/4 of the sunlight for about 6 years. The impact also possibly accelerated the already large volcanic eruption event in the Deccan Traps in India on the other side of the planet, which spewed a tremendous amount of matter into the atmosphere as well. These events combined to lead to a massive extinction event. The evidence of this asteroid's global impact is seen in the lower picture by what's called the KT boundary, found everywhere around the globe. It's where the rare element iridium was deposited in vast amounts all over the world, indicating an extraterrestrial impact, since this element is not found in any large quantities on Earth. It had to come from somewhere. This major extinction event included the dinosaurs, which were the rulers of the Earth at the time, but when they went extinct, that allowed underground mammals to flourish and eventually, over a long, long period of time, evolve into our species. So in one way, we can say yay for asteroids, otherwise we wouldn't be here. Just for reference, the Permian extinction that we talked about, related to the most massive Antarctica crater, was the third major extinction event, and the dinosaur extinction event was the fifth out of 5 completed extinction events on Earth that we have found evidence for in the last 440 million years. Scientists theorize that we've begun a 6th mass extinction event, this one due to human activity rather than an impact event, which means this one, if not reversible at this point in time, is at least able to be mitigated to avoid the worst outcomes, unlike an impact. So how do we keep another impact from happening again? Fortunately, we have increasingly detailed technology to help us avoid an outcome like asteroid-prompted extinctions. Ground-based telescopes continually scan the night skies and are the first to spot asteroids. You can see the asteroid in the left image moving from the upper left to the bottom right across the field of stationary stars. Measurements taken from ground-based telescopes like Arecibo was highly used. That's the one in Puerto Rico for this. Measurements lead to orbit calculations. Then astronomers can add those objects into a tracking system and continue to study it. And this radar is then used to characterize the object, helping to refine those calculations. Radar gathers a wealth of information: shape, size, texture, spin rate, speed, distance, all helping to calculate and predict an object's movement over time. Unfortunately, setbacks in tracking occur. Look carefully at all the towers and connectors strung across the main dish here at the famed Arecibo Observatory in Puerto Rico. This is what it looked like after a massive collapse from lack of infrastructure maintenance last December. Very, very unfortunate. But meanwhile, there are other programs at work to protect Earth from random interlopers from space. NASA's Planetary Defense System has a vast arsenal. It's built to find, track, and deflect near-Earth objects. This team is constantly watching the sky to find and track potential hazards. This team says there are no known asteroid threats to Earth for at least 100 years, but that doesn't mean we're not looking. Note the types of missions listed here in white and the names of the specific missions in blue that will achieve these goals. We'll take a look at one of them in particular in a minute, the DART program. CNEOS, that we talked about before, the Center for Near-Earth Object Studies, has a really interesting website. And speaking of that, I have put together a whole bunch of links related to the things in this presentation. And Ms. Uma will throw those into the chat for me as well. This is one of them, so it's worth looking into. There's loads of data on these near-Earth objects and how they're tracked. You can see this list with the year of closest approach and the probabilities of impact without any deflection attempts. Note line 2 is the asteroid Bennu. Let's take a look at a mission specific to this object. OSIRIS-REx went to the asteroid Bennu. It arrived in 2018, collected samples successfully, and is on its way back to Earth, which is all really cool. Scheduled to land here back on Earth in 2023. So it will be very exciting to get the samples back from that. Bennu is dark, therefore it's harder to detect out in space. So this mission gathered more data on composition and density to analyze the best methods for deflection if it were decided that this type of asteroid were a threat in the future. There was also something surprising in the data. Because Bennu is dark, scientists were puzzled by glints of brightness on its surface in initial observations. OSIRIS-REx was able to gather and analyze enough data to determine that those glints on its surface, on the surface of Bennu, were actually small pieces from another asteroid in the main asteroid belt, the second largest, named Vesta. This was invaluable data in helping to understand how our solar system was formed. And in those links I mentioned is a pretty neat little video that NASA put together on how they discovered this in particular. DART, or Double Asteroid Redirection Test, is another upcoming mission to actually test deflection methods. The DART spacecraft will travel to a double asteroid, an asteroid named Didymos that has its own moon named Dimorphos. It will then impact with Dimorphos in an attempt to change its trajectory. Impact is scheduled for September 26th to October 2nd of next year, 2022. Here's a quick comparison of sizes. You can see how small DART is DART's impact with Dimorphos is expected to change the moon's velocity by 1 centimeter per second, which should be enough to alter its trajectory and its orbit over time. DART launched really recently. It just launched on November 23rd. This is the path that DART will take to engage with Dimorphos late next year. It will carry another autonomous mini satellite, or what we call a CubeSat, that Lycia cube on the left side of the screen. That will be deployed before impact, and it will record the impact as it happens. CubeSats are extremely small and versatile, and NASA has a lot of them as tools in their arsenal. This just gives you an idea of how small that little thing is that DART will be deploying. There are also 2 additional follow-up missions to the DART mission scheduled in 2022 and in 2026. So back to the Lucy mission. Remember Lucy? This diagram shows the orbits of Venus, Earth, and Mars in the center, and Jupiter, the white ring. The main asteroid belt is not shown here, but we can clearly see the Trojan clusters leading and trailing Jupiter in Jupiter's orbit. Those are the targets of Lucy's mission. Lucy launched in October and will examine at least 7 asteroids in both the leading Trojan cluster and the trailing Trojan cluster. Earth's gravity is used as a slingshot. So you can see the red blob moving around. That's a depiction of Lucy. It comes close to Earth and then speeds up, and part of Earth's gravitational pull basically slingshots it around. And they have calculated this so carefully that it can do a number of these orbits around Earth and intersect with very particular asteroids. They have named 7 asteroids that it will interact with. But before it gets to the leading and trailing Trojans, Lucy's first target is a dress rehearsal. And it's not shown here, but it's a very small asteroid on the near side of the main asteroid belt named Donald Johanson. And it's an aptly named asteroid because Donald Johanson was the paleoanthropologist who discovered the Lucy fossils in Ethiopia. Okay, so detailed data that Lucy will collect from these asteroids will include size, mass, composition, with special attention paid to ices, geologic features, interiors, and origins. We'll collect a lot of data. Lucy is a pretty small spacecraft, only 50 feet across when the solar arrays are deployed. That's one of the solar arrays in the clean room. And this is just a quick little video that shows how they deploy those arrays. The little squares are the solar cells, and then the yellow-orangish fabric is just what they're mounted on to allow it to fold and unfold as needed. Pretty cool stuff. So how can we know when and where to look for all these objects? The annual meteor showers that we talked about are well documented. The best information that I have found on them is located at earthsky.org. That's also in the links for you. They have a tremendous amount of detail on each annual meteor shower. Keep an eye on the sky in January for one of the best shows of the year. If you aren't one to hang out in the cold, wait until the August Perseids for another top annual show. Those are the 2 biggest ones every year. I also recommend at the bottom links and notifications to spot the International Space Station regularly in the sky. The ISS passes over quite often, even though its orbit moves over Earth's surface and it passes over in different places and different times, the speed required to stay in orbit and not fall towards Earth is 17,500 miles an hour. That's how fast the space station has to go in order to stay in orbit. So it only takes 90 minutes to orbit Earth once. This website down at the bottom, the www.spotthestation.nasa.gov, has a ton of good information. I will come back to this chart in a minute for you, but I want to show you that website, a screenshot, the lead screenshot from that. Notifications of the ISS passing with visibility range to where you are include where in the sky to look. So you have to be able to measure angles up from the horizon. The angle of visibility above that horizon is really easy to calculate. So the horizon is 0 degrees. Straight overhead is 90 degrees. Your fist at arm's length equates to about 10 degrees of sky. So if you extend your arm straight out, straight elbow, line up the bottom of your fist about where the horizon is, you should be able to do fist over fist and get 9 fists to be straight overhead. It's just a really easy way to measure that, especially if you're out in the dark. So one of the other things I suggest down in the lower right for constellation viewing, I suggest getting a star finder. They're sold, you may think that a lot of people may think this is a little old school, but they're really good. They're sold at bookstores and online. I suggest supporting your local bookstores. They look like the image in the bottom right corner, or the link there, spaceplacenasa.gov, will show you how to make one yourself, which is a lot of fun, especially if you have kids or you are one at heart. The apps, Star Walk 2, that's my favorite, and Stellarium are also really, really good. I would like to share one last favorite anecdote with you from Commander Chris Hadfield. He is actually part of the Canadian Space Agency, but I tend to think of him as one of our own local astronauts because he's from Sarnia, which is right across the river from Port Huron. He made a lot of trips to space before retiring a couple of years ago, but he's well known for his solo guitar singing rendition of David Bowie's Space Oddity while floating in the space station, as well as for his quick wit. Earlier in his career, he explained how some personal processes work in space at a news conference. This really is relevant to tonight's topic, so please bear with me. When astronauts deal with bodily outputs, you may know that urine gets recycled into drinking water, a very well-known and safe process to deal with. But solid body wastes are a harder problem to deal with. So they collect it and they store it in a small cargo container, exposing it to the vacuum of space so it essentially freeze dries, so there's no odor, no bacteria. When the container is full, they undock it and let it fall towards Earth, where it burns up in the atmosphere. So the next time you see a beautiful meteor, that's what it could be. I want to thank you all for your interest in the night skies. Remember that everything is connected and keep looking up. With that, I will kick it back to our moderator.
Oh, thank you very much, Terry. It was wonderful presentation. Very good, useful information, very, very useful information, what we didn't even know what's going on in space. When you were talking about NASA and all that, I would like to share my experience that I worked in India. When I started my career as a teacher, I worked in ISRO, ISRO, Indian Space Research Organization, as a teacher in those schools. And I really saw this rocket launching in person and those control rooms and So all these things, and now I'm refreshing all my memories. And also I would like to share with you this rocket what they gave me as a model, PSLV. So this is what I'm just holding it on to this, because that's a good memory of that. I worked there, and that's an excellent memory for me, that. And really now it's a great science. Astronomy is something, it's really great science. And I cannot understand what's going on into space, and you really explained it well. I hope everybody has enjoyed it. I have also shared all the links that you requested me to share with everyone. I have shared with everyone here. I posted. And if some people, if you cannot get it, I will be able to email to you as well. Definitely, I'll email to you. And thank you very much. I have not seen any questions in question answers box and also in chat box. Nope, nothing is here. I don't think they have any questions yet. We really enjoyed it. Thank you very, very much again, Terry.
You are very welcome.
And everybody who has attended this program tonight, thank you very much. Stay safe. Happy holidays to everyone.
Likewise. Thanks so much.
Bye. Thank you, Terry.